I have already talked a bit about the pH scale in a previous video in this series. You will find a link to the playlist in the description, and I recommend you watch at least video number 4, Chemistry of Aqua, before you watch this video. But as already mentioned in that video, the pH scale runs from 1 to 14 and displays the range of acids and bases from top to bottom. An acid is measured at 1 to 6 on the pH scale, while bases measure somewhere between 8 to 14. In order for a substance to be considered neutral, it needs to have a pH of 7. pH itself is a term that stands for potential for hydrogen ion concentration. It's a logarithmic measurement of the amount of hydrogen ions in a solution. The greater the concentration of hydrogen ions in a solution, the lower the pH will be. Conversely, the pH will be higher if the concentration of hydrogen ions is lower. Acids and bases play a huge role in your everyday life. In fact, you wouldn't even be alive if it wasn't for the underlying chemical mechanism of acids and bases, but more on that later. Not only does an acid help you digest the food you eat, but what are acids and bases really? We'll begin by explaining what an acid is. Although reality is a lot more complicated, here's a very simplified version of what an acid is. An acid is a substance that increases the concentration of H+, hydrogen ions, or protons, in a water solution. The standard reaction for an acid if it's dissolved in water, such as hydrochloric acid, is a water molecule plus hydrochloric acid gives an oxonium ion and a chloride anion. As you might have guessed, the more oxonium ions that are produced, the smaller the pH will be. In other words, the more oxonium ions that are produced, the more acidic the water will be. That's because in a water solution you will never find any free hydrogen ions or protons. They will always be bound to a water molecule. When an acid gives away a hydrogen ion or a proton to another substance, we say that the acid is protolyzed. Another way of describing it is to say that the acid is deprotonated. An acid is corrosive if the concentration of H+, or protons, is big enough. The reason for this is that proton exchanges to any substance or material in question will break it down and make it more soluble in water. On our tongues, there are receptors that feel the concentration of these hydrogen ions or protons, so we can sense how sour something is. A strong acid is defined as an acid where most of the molecules give away its protons. Some of these are nitric acid, sulfuric acid, and hydrochloric acid, which also is found within your stomach. Strong acids can break down most substances, even metals. Not even noble metals like gold is necessarily safe. Gold will not be dissolved if it's exposed to one of these strong acids by themselves. However, if you mix nitric acid and hydrochloric acid, this results in something called aqua regia, which is infamous for dissolving gold. Some acids are diprotic, meaning it can release protons in 2 steps. An example of this is sulfuric acid, although the second proton is usually not as easily given away as the first one. Some acids are triprotic, such as phosphoric acid, which you will find in many sodas, such as Coca-Cola. On the metric between weak and strong acids, phosphoric acid is somewhere in between. The phosphoric acid in the soda is not going to hurt you as long as you don't have too much of a contact with it. However, it's not just the sugar, obviously, that's dangerous for you if you decide to keep Coke in your mouth for too long. When you dissolve a weak acid in water, only a small part of the acid molecules will actually deprotonate. A common number of how many percent of those molecules in a weak acid that will give away its protons is about less than 2%. So the pH doesn't get as low as it would be with a strong acid instead. Some examples of weak acids are carbonic acid, which you will also find in soda. Another example is ethanoic acid, also called acetic acid. Metallic ions such as aluminium 3+ can also be an acid. What happens is that the metallic cation binds up water molecules, and one of these will release a hydrogen ion or a proton. To describe how strong an acid is, you use something called the acidic dissociation constant, which is written as a K with a small a. Because of the small values that the minus logarithms can give with Ka, pKa gives us numbers in a context that we can more easily work with. Some examples are shown here. A base is a substance that can take up these hydrogen ions or protons from acids or regular molecules. A requirement is that the base has a free electron pair to take up a proton. A classic example of a base, which is also a strong base, is sodium hydroxide. OH- is called hydroxide ions, and these are the ones that give water its basic properties. The more OH- there is in a solution, the smaller the amount of H3O+ there will be, which means that pH will increase. A base is corrosive just like acids, and mostly for molecules that are organic. If you've ever felt a base on your hand, it feels soapy. And that's because the base is dissolving fats in your skin through something called basic ester hydrolysis. In the process, it forms fatty acids, very much like the ones that you will find in soap. When you dissolve a weak base in water, only some of the basic molecules will take up protons from that water. The pH isn't as high as it would be if you dissolved a strong base. An example of a weak base is ammonia, NH3. A neutralization means that an acid and a base react in such a way that their former acidic and basic properties are neutralized, therefore the name. What remains is a salt and eventually water. However, a neutralization reaction doesn't always create water. One example is ammonia and hydrochloric acid. This creates salmiak, which you may recognize as that licoricey taste. An ampholyte is a substance that can act both as an acid and a base. Like I already mentioned in my previous video, Chemistry of Aqua, water is such an example. But there are others too, like hydrogen carbonate, hydrogen sulfate, hydrogen phosphate, and dihydrogen phosphate. Acidic and basic pairs are different versions of the same molecule where it in one form is an acid and the other a base. A buffered solution is usually a water solution that contains a weak acid and its corresponding base in some proportion. The function of a buffered solution is to keep pH stable. If the pH in the solution is raised, this will be compensated by the weak acid giving off H+ or protons and will lower the pH again. If the pH is decreased, the base will take up the H+ or the protons and the pH will increase again. Buffered solutions are not just used in the lab, but they are actually utilized in many living organisms, you included. In our bloods, we have a buffered solution that keeps the pH in a very narrow range. If our blood becomes too basic or too acidic, we will not survive. The normal pH of human blood is 7.4, and deviations of even a few tenths of a pH unit can be fatal. For instance, in living organisms, carbonic acid and bicarbonate ions are very important to keep our pH at the same level. Buffers illustrate the reversibility of chemical reactions. Addition of acid drives the reaction in one direction. Addition of base drives it in the other. The significance of acids and bases are not just found in living organisms, however, but the very ground you're walking on. Believe it or not, but the fact that you're not disappearing in a sinkhole right now as you're watching this might very well be due to pH levels in the soil. The underlying bedrock of many landscapes is usually limestone. Limestone is composed of calcium carbonate, which primarily comes from the remnants of corals and other types of marine organisms. Their shells are made of calcium carbonate. Calcium carbonate is also found in the shells of eggs. You can perform a simple experiment. Take an egg, place it in a glass of vinegar, which contains about 5% acetic acid or ethanoic acid, and you will notice little bubbles of carbon dioxide gas from almost immediately. Give it a few days and the eggshell has pretty much completely disappeared. Substances that are made of calcium carbonate will react with an acid. As such, limestone, for instance, is slowly worn away due to acidification of our rain. The biggest contributor to acidic rain is actually power plants where they burn coal. The reason for this is that the coal that is burnt is not just pure carbon, but actually contains some amounts of sulfur. Sulfur is very acidifying, and when it gets into the atmosphere, it gets dissolved in the water droplets that then fall to the ground as rain. However, the rain is acidified regardless if it encounters pollution or not. The reason for this is that as the raindrops are passing through the atmosphere, they get into contact with carbon dioxide. As the carbon dioxide gets dissolved within these water droplets, carbon dioxide is turned into carbonic acid, and the pH of the water in the droplets goes down to about 5.6. The carbonic acid in these droplets then dissociates to give a proton and a bicarbonate ion. Acidic rainwater seeps into the ground and comes into contact with limestone bedrock. The water makes its way into cracks and pockets of the rock, and as such it reacts with the limestone and eventually makes holes and fissures in the rock. This is one of the reasons why sinkholes have become more common as of late. And in a state like Florida, where the bedrock is almost entirely made out of limestone, this can be disastrous.
After 10 wet days, more than 17 inches of rain fell in parts of Florida, and it keeps coming. Conditions perfect for sinkholes, and that's exactly what's happened. In the last 2 weeks, more than 30 sinkholes in central Florida.
Makes me real uncomfortable even going close to my house.
They got a lot of work to do to fix this up.
In some cases, sending a warning signal of what's to come.
There were other warning signs too, but the residents who live along the golf course here at the Villages didn't know how to read them. In a matter of moments, without warning, the lake here went dry. Geologists say it was the clearest indication of what was to come.
In the Villages, where 2 houses are now condemned, that small divot in front of the Flegler's home leading to the same question every morning this week.
How's the hole? Was it any bigger? So not needless to say, it's always in the back of your mind.
Because you're not really given much of a warning by Mother Nature, are you?
No, we're not.
Here in what's called Sinkhole Alley, the fear tonight is more surprises like this.
In the last 24 hours, 6 new gaping holes have opened up here in Ocala. With a storm brewing in the tropics, that means more rain will drench this area, meaning that these holes may get larger and new ones could develop.
There is one interesting consequence of this, of course. The process I just described is also how most caves in the world are formed. Yes, most caves in the world are formed through acidic rain. Most caves in the world actually started as a sinkhole. And as the water continues to fall down the sinkhole, the shape of the sinkhole actually helps to channel the water to a specific area, opening the bedrock even more as the limestone is being corroded. The process of acidic rain may seem destructive, and make no mistake, it is, but it also creates these unique environments underground, massive caves where we find new and exciting species. However, as our rain becomes more and more acidic due to our air pollution, we may not just have a situation where we are undermining the literal ground we walk on, but also our cultural heritage. A lot of World Heritage sites are actually in danger because of the acidification of rain. A vast amount of ancient buildings, as well as statues, are at risk of being literally dissolved before our eyes due to acid falling from the sky. However, acids are not just destructive in nature, you literally need them to be alive. There are 20 amino acids that you need to build protein in your body. These amino acids have a C-terminal and an N-terminal, and due to their chemistry they can join together and form proteins. What underlines all of this is the chemistry of acids and bases. Since acid and base chemistry play a vital role in the chemical reactions that happens in your body all the time to keep you alive, it may not be a surprise that it's very relevant for the food you eat as well. Different foods have different pH levels on average. A lemon has a pH of about 2, which is pretty sour. Corn is pretty neutral at pH 7, and a banana has a pH of about 5. Foods also contain acid and base precursors. A precursor is something that comes before something else, or in science it can be a substance that is eventually converted into another substance. Meats contain a lot of acids that are good for you because, as I mentioned before, amino acids build up protein. Sulfur is therefore called an acid precursor because it is converted to sulfuric acid in your body. Protein from animal foods has more sulfur than protein from vegetable foods, so if you eat a lot of animal protein, then your body is producing more acid than someone who eats food with vegetable protein. Certain foods, such as vegetables and fruits, contain base precursors. A good way to determine how many base precursors are in a food is to look at the potassium content of the food. Potassium has a positive charge and is attracted to negatively charged molecules that are base precursors. Many of the negatively charged molecules associated with potassium are converted to bicarbonate, which is a base. The body breaks these compounds down to potassium and bicarbonate, which is used to neutralize acids in your body. Any bicarbonate that isn't used up is actually stored in your bones. This is also why you shouldn't eat too many foods that contain acid precursors. What happens is that your body can take some hydrogen carbonate from the stores of your bones to neutralize the acidity that comes from eating too many foods with acid precursors. As a consequence, this can actually contribute to bone loss. I think I've gone on for long enough now in this video, and I will stop it here. But just remember that acids and bases are not just molecules that are caught in a never-ending game of tennis playing around with a proton. But acid and base reactions are actually vital, fundamental for keeping you alive. Even the rigidity of the ground you're walking on is dependent on acids and bases. One could quite literally say, the ground beneath you will literally fall apart. Whether it is the water you drink, the ground you walk on, the food you eat, or the blood that's pumping around in your veins, it's all due to the chemistry of acids and bases. The chemistry of sour and bitter.